Hello, students. Have you ever noticed how some cleaning agents have a sharp, sweet smell while others have no smell at all? That difference often comes from the presence of halogen atoms in organic compounds. Pure alkyl halides are usually colorless, but bromides and iodides darken when exposed to sunlight. Many of the volatile halogen derivatives carry a sweet odor, which is why some early anesthetics like chloroform smelled almost pleasant. And LT, break time is equal to 0.5 SNGT. The physical properties of halolcanes and halorenes are controlled by factors like polarity, molecular mass, and intermolecular forces. And LT, break time is equal to 0.5 SNGT. These properties explain why halolcanes behave differently from their parent hydrocarbons, with higher boiling points, different densities, and very limited solubility in water.
Now let's focus on melting and boiling points. Small haloalkanes such as methyl chloride, methyl bromide, and ethyl chloride are gases at room temperature. As we move to higher members, they become liquids and eventually solids, because larger molecules have stronger van der Waals forces. Boiling points of haloalkanes are significantly higher than hydrocarbons of similar mass. For the same alkyl group, the order of boiling point is alkyl iodide, greater than alkyl bromide, greater than alkyl chloride, greater than alkyl fluoride. This happens because as we move down the group, the size and mass of the halogen increases, strengthening intermolecular attractions. Another factor is branching. A branched isomer has a lower boiling point than its straight-chain counterpart, because branching reduces the surface area available for molecular contact. That is why 2-bromo-2-methylpropane has a lower boiling point than its isomeric straight-chain bromides. Among isomers, branching is not the only influence. In haloarenes, particularly dihalobenzenes, the melting points of ortho, meta, and para isomers are quite revealing. While the boiling points of these isomers are nearly the same, the para isomers have much higher melting points. The reason is symmetry. Para isomers pack more efficiently into a crystal lattice, leading to stronger intermolecular forces in the solid state. So, although all three dihalobenzenes boil around the same temperature, the para isomer stands out with its higher melting point. This kind of property difference often comes up in competitive exams, so keep it in mind. Now, what about solubility? Haloalkanes are only sparingly soluble in water. To dissolve in water, they would need to break strong hydrogen bonds between water molecules. But the new dipole-dipole attractions between haloalkane and water are not strong enough to compensate. As a result, their solubility is very low. However, haloalkanes dissolve readily in organic solvents such as benzene, ether, or alcohols. That's because the intermolecular forces in haloalkanes are of similar strength to those in organic solvents. The principle of like dissolves like works beautifully here. Let's look at density. Haloalkanes generally get denser as the halogen becomes heavier. Most chlorides are lighter than water, but bromides, iodides, and polyhalogen compounds like chloroform and carbon tetrachloride are denser and sink in water. Density also increases with the number of carbon atoms and the number of halogen atoms in the molecule. For example, dichloromethane has a density of about 1.336 grams per milliliter, chloroform about 1.489, and carbon tetrachloride 1.595, all heavier than water. Let's apply this knowledge in a worked-out example. Arrange the following compounds in increasing order of boiling points: bromomethane, bromoform, chloromethane, and dibromomethane. Step 1. Compare molecular masses. Chloromethane is the lightest, so it has the lowest boiling point. Bromomethane is heavier, so it comes next. Dibromomethane is even heavier and therefore has a higher boiling point. Finally, bromoform, with 3 bromine atoms, is the heaviest and has the highest boiling point. So the order is chloromethane less than bromomethane less than dibromomethane less than bromoform. Notice how the number and type of halogen atoms directly control boiling point through van der Waals interactions. Let's summarize. Haloalkanes are generally colorless, though bromides and iodides darken on exposure to light. They have higher boiling points than hydrocarbons, following the order Ri greater than Rbr greater than RCl greater than Rf. Branching lowers boiling points, while para-isomers of dihalobenzenes have higher melting points due to symmetry. They are poorly soluble in water, but dissolve well in organic solvents. Density increases with the size and number of halogen atoms, making many bromides and iodides heavier than water. So, the physical properties of haloalkanes and haloarenes are not random. They reflect the balance of polarity, molecular size, and intermolecular forces. Keep these trends in mind because they form the basis of how these compounds are used in industry and laboratory practice. I hope today's session made you see the connection between molecular structure and physical behavior. See you next time with more exciting chemistry concepts.